Thank you for coming to listen to me. I'm Shiki Ueoka. I will explain my new theoretical framework for the critical phenomena of the Anderson transition. Like other phase transition, the Anderson transition is also driven by the strength of disorder and exhibits power law behavior. Regarding the localization length, the critical exponent nu that appears in the power law is called the critical exponent. The critical exponent is expected and believed to have universality. In other words, the critical exponent is believed to depend only on the symmetry and the dimensionality of the system, not on the details of the system. In this research, we focused on a class of symmetry called the orthogonal class. Its typical Hamiltonian is given by this equation. It consists of a random on-site energy term and a nearest neighbor hopping term. When we talk about dimensions, we generally think only of natural numbers, but in research of fractals and random walks, dimensions that takes real numbers are considered. Spectral dimension ds is real number dimensionality defined by the probability of random walk on lattice starting from x and end with y after t steps. Because the critical exponent depends on dimensionality, the critical exponent nu seems to change continuously about spectral dimension. Therefore, we should understand the critical exponent nu as the function of the spectral dimension, but not only as specific value of integer dimension. In this point of view, we need to construct the theory of critical phenomena such that the definition of the real numbers dimensionality becomes clear. One possible way is to start from concept of random walk. I use random walk expansions of the green functions. Here gamma dxy is a set of paths which starts at site x and ends with y with number of steps t. Sharp gamma alpha is the number of visits to site alpha for path gamma. To extract information about localization lengths from the random walk expansion, we need to relate the expansion with spectral expansion. If only the dimensionality is relevant for the critical phenomena, I may assume summation over typical path plays relevant role. Here AXYT is the number of statistically typical paths. VJT is the distribution of the number of visits by a statistically typical path. Uij is the independently and identically distributed random variables. To extract localization length psi by comparing to these two expressions. To take exact summation is still complicated, so I decided to use high-dimensional approximation as first step to make a new theory. This approximation is I set v1t equal t plus 1 and others vjt is set to be equal to 0. Then we consider two cases. One is paths which starting point and end point are far apart. The other case are close. Each green circle represent diffusive paths, so they are typical paths. This calculation is based on random walk theory. Description by diffusion phenomena is used in previous slide, so we need to define diffusion constant in any way. Anticipating the conclusion, to get nu equal half at d equal infinity, I assume this expressions for form of diffusion constant. Then after some calculations, I got expansions of Green's functions based on random walk theory, picking typical paths with high-dimensional approximation. From here, I used several approximations, but they were based on random walk theory, and it means that I just used information of dimensionality. Therefore, I expect that these approximations may not be problematic in terms of the critical phenomena. To check this theory, first I tried numerical check of this new theory by choosing cutoff suitably to get gxye is proportional to e as e approaches to 0 by Paddy approximant as first aid. I got estimate of the critical exponent with infinite size system numerical simulation, and it is consistent or slightly smaller than previous studies. Second, I tried analytical approach by averaging summation in Cn about binomial coefficients and remain terms with t greater than or equal than L. I got this equation for localization length. Here A is proportional to 4k over W. Again, Paddy approximant for as first aid gives the new approximate expressions of the critical exponent nu, the number of several terms as long as I checked. This result does not depend on the number of terms and the value of coefficients of expansions Fj. In other words, details of systems. This suggests that this new theory may prove universality of the critical exponent. Besides it, this formula gives not too far estimate of the critical exponent nu compared with previous studies. This is best a theoretical estimate without summation method or cutoff at present. The possibility of this kind of direct proof of universality is a typical result of this new theory. In summary, first, it is necessary to study critical phenomena with real number dimension based on random walk concept. I named this new theoretical approach for the critical phenomena as statistical random walk summation method, SRWS, or SRWS data theory. Second, SRWS with Paddy makes it possible to simulate infinite size system and high-dimensional systems or non-integer dimension system quickly and effectively, and gives almost consistent result with previous studies. Third, a kind of zeta functions phi and zeta functions appears in approximate formula of psi and nu. This suggests that the number theory relates with the critical phenomena. For example, the critical exponent nu diverges at the lower critical dimension because infinite number of prime numbers exists. Thank you for your listening.